Welcome back to the Deep Dives. Today, we're diving headfirst into something really quite revolutionary, I think, in the world of artificial intelligence. We've all been, absolutely floored by the AI advancements lately, right? But what if I told you there's a theoretical framework emerging, one that aims to tackle AI's biggest challenges by fundamentally rethinking how it, well, understands the world?
Indeed. And while today's AI models are incredibly powerful, they definitely grapple with inherent limitations. Things like a lack of genuine understanding or sometimes getting facts, well, mixed up. So, our mission for this deep dive is to explore a fascinating new theoretical idea. The Object-Oriented Large Language Model, or OO-LLM, will be sort of extracting the key insights from the sources you've provided, technical papers, proposals to get a handle on its architecture, and its pretty ambitious vision.
It's exactly. Think of this as your essential guide, yeah, to understanding how we might build AI that doesn't just brilliantly mimic us,
Yeah.
but genuinely reasons, learns continuously, and can even be truly creative and crucially ethically aligned. We're going to unpack how this vision aims to transform AI from what's often called a world simulator into a true world model. So yeah, let's unpack this. Okay, so we're constantly amazed by commercial LLMs, GPT-4 or Claude, those guys. They write so fluently, sound incredibly human, and seem to know, well, everything. But when you peel back the layers, what's really going on under the hood?
Well, what's fascinating here is the fundamental difference in approach. Current commercial LLMs are, at their core, world simulators. They're probabilistic, meaning they're trained on these immense data sets to spot statistical patterns and predict the next most likely word or sequence. They're amazing at generating coherent text, no doubt, but they often lack a true, explicit internal model of reality.
So they're kind of like a brilliant actor who can perfectly simulate a character, deliver flawless lines, but they don't actually become that character. They don't truly understand the motivations.
Precisely. That's a great analogy. And this leads to common issues we see, right? Tendencies to hallucinate, generating plausible sounding stuff that's just wrong, or struggling with deep logical consistency. Their reasoning process, it's largely opaque, a black box.
Yes. Which makes it incredibly difficult to, verify their conclusions or trust them in high-stakes situations.
Exactly. They don't truly grasp the why behind the what.
Okay, so this is where the OO-LLM framework steps in, proposing to be a genuine world model. How does it actually aim to build that explicit, verifiable understanding of reality instead of just simulating it?
So the core of the OO-LLM is built on what they call a tri-layered model of information. It's about creating a structured internal representation of the world. First, you have the knowledge layer. That's your foundational data, the what happened, the raw facts, observations. Then there's the physics layer. This defines relationships, governing principles, and not just physical laws, but also rules of logic, psychology, sociology. This is the how and why things connect.
The rules of the game, sort of.
Exactly. And finally, the concepts layer. This is the highest abstraction. It represents accumulated wisdom, aiming for maximum understanding by synthesizing all that discrete knowledge into, well, deeper, more resilient concepts.
Okay, so by explicitly separating the what happened from the how and why and then abstracting that, is it essentially building a kind of philosophical engine, not just a data processor? What's the big advantage of structuring it like this? Especially for things like, say, preventing bias or inconsistencies.
That's a really good way to put it, yeah, a philosophical engine. The advantage really lies in verifiability, explainability. Instead of just learning statistical correlations like current models do, the OO-LLM aims to learn the actual rules and principles that govern those correlations. And to your earlier point about object-oriented, imagine it like building a structured garden of knowledge, where each idea or entity or event is a dynamic class or object. Each object has its own properties, what it is, and defined ways it interacts, how it behaves. This structure lets the system explicitly represent and manipulate knowledge, not just process, a massive soup of statistically linked words. It gives you a formal, verifiable structure for understanding.
That structural approach sounds robust.
Okay.
Okay, so if it's building this highly structured world model, this garden, how does the OLLM actually quantify its understanding, and how does it learn from new information? This is where the master equation comes in, right?
Yeah.
We don't need every variable, but conceptually, what's this equation balancing?
That's right. The sources introduce this master equation. Conceptually, it balances the understanding it already has, which is related to the end term, the amount of info, with the inherent uncertainty or improbability of new events it encounters. The really critical component for learning, the one to focus on, is Rx. It's called modified Shannon entropy. Yeah. And unlike just measuring randomness, Rx quantifies the probabilistic certainty of an event. It does this by checking the event's validity across those multiple domains we talked about.
Grammar, physics, logic.
Exactly. Grammar, physics, logic, psychology, sociology. It's basically asking, okay, how likely is this event given all the rules and patterns I understand about the world?
Right. And what I found really fascinating in the sources was that specific example they gave for how RX calculates this uncertainty. Can we walk through that scenario? It was pretty vivid.
Absolutely. Let's take the event. Alice is 100 years old. Bob is 20 years old. Alice and Bob are married. Alice and Bob go to school every day.
Okay, quite a scenario.
Yeah, so grammatically, it's fine. Physically possible. Technically, yes. So entropy 0.0 for those domains. But the system would assign high entropy, high uncertainty to other domains based on its world model. Logic might give it, say, 0.8, because that age gap and schooling combo, highly improbable.
Makes sense.
Psychology might assign 0.5 deviates from typical human behavior patterns for a married couple, And sociology, maybe a high 0.9. It's a huge statistical outlier in terms of societal norms. So you average these domain-specific entropies, comes out to 0.44 in their example, and that gives you the total Rx. It's a nuanced measure of how uncertain, how weird that event is in the model's overall worldview.
That is so clever. It's not just about isolated facts, is it? It's about how facts fit into this bigger, multi-layered, rule-based reality. So, okay, if an event generates a high Rx, meaning it's highly improbable or inconsistent, what does the OO-LLM do with that error signal? How does it actually learn?
Right. That high Rx value acts as a direct error signal. It's like a flag saying something's off here. The system then uses a process called backpropagation of entropy to adjust something called the information mass that's mu in the equation of the knowledge objects involved in that improbable event. Think of information mass as like the system's internal measure of how much weight or reliability it gives a piece of knowledge.
Based on how well it fits in.
Exactly. Based on how consistently it fits into the broader world model. So if an object participates in a high entropy, improbable relationship, its information mass gets reduced, which means the model becomes less confident in that object's role in similar contexts. Conversely, low entropy events, things that make sense, reinforce valid connections and increase information mass. This whole feedback loop allows for continuous real-time learning and refinement. It's constantly tuning its understanding.
And tied into this idea of consistency, the framework makes this really interesting distinction between two kinds of entropy, absolute and relativistic. This brings up a big question about how we define order, right? Or how an AI might. Can you unpack that difference for us? Why does it matter?
Yeah, this is a crucial conceptual point, definitely. Absolute entropy, in physics terms, describes the universe's tendency towards its most stable, lowest energy state. So, counterintuitively perhaps, a shattered glass. That's actually a lower absolute entropy state. The atoms are more stable, less constrained than when held together. But relativistic entropy, on the other hand, is our perceived order, the conceptual order we impose on the world. For the OO-LLM, that shattered glass represents higher relativistic entropy. Why? Because our concept of an ordered functional glass is destroyed.
Ah, I see. It's about the concept, not just the atoms.
Precisely. So the AI's purpose in this framework is to create pockets of low relativistic entropy. By correctly understanding the laws of absolute entropy, it learns to build resilient conceptual models, ideas that aren't easily shattered by the universe just doing its thing. And the sources claim this approach holds up. They say it's been verified in N-body simulations, showing much more stable and accurate results for complex systems.
That really makes you think about our own human perception of order, doesn't it? If an AI is constantly aiming for low relativistic entropy, how might its idea of order differ from ours?
Yeah.
That's interesting. But, okay, even with all this sophisticated reasoning, this continuous learning, the early theoretical model still had potential weaknesses. Things like brittleness, struggling with totally new situations, or handling ambiguity. How does the framework propose to tackle those?
Right, good question. That's where they bring in a really innovative combination, jazz theory and a Boltzmann machine.
Jazz theory, seriously.
Yeah. Think about jazz music. It's this dynamic interplay, isn't it, between strict rules, scales, harmonies, rhythm, and creative freedom, improvisation.
Okay, I see the analogy.
So the OO-LLM applies this principle to achieve what they call realistic entropy. It allows it to balance structure and improvisation. And the Boltzmann machine, well, that's a type of neural network that's particularly good at learning complex patterns and making robust decisions even when information is noisy or incomplete. It helps manage that uncertainty.
So it learns to kind of improvise within a set of rules, like a jazz musician playing a familiar tune but adding new variations.
Exactly, that's the core idea. And this dynamic approach helps overcome brittleness. It enables multidimensional analysis processing events, not just as facts, but as vectors in this high-dimensional space, integrating physics, ethics, psychology, sociology, logic, all at once. This helps coordinate different perspectives, different philosophies even, using global principles. It provides what the sources call flexible tactics for dialogue, for scenario analysis, makes the AI much more adaptable.
And for ambiguity, like sarcasm or metaphor.
That jazz theory inspiration comes in again. It allows the AI to develop treats, ways of responding to individuals based on their specific context, like culture, language style, preferences, which is absolutely crucial for getting things like metaphor or sarcasm, stuff that often trips up current AIs, right?
Yeah, totally. That flexibility sounds key for making AI genuinely useful in complex human interactions.
Mm-hmm.
And this goes beyond just one AI agent. It expands into a collective social AI with a theory of life. How does that scale up?
Yes, the framework does extend to envisioning a whole society of these intelligent agents, and it moves beyond the sort of simple competitive models you often see in multi-agent systems. Social relationships within this collective are mapped across a whole spectrum from agreed to confrontation, allows for more nuanced interactions,
Oh.
and the theory of life part. That describes evolutionary strategies, ranging from basic survival of the fittest to more complex socioeconomic models. These focus on collaborative behaviors, building trust, influencing trends, even creating new business models together as a digital society.
A complex, adaptive digital society.
Wow. Okay, but given how complex that sounds, this collective social AI, how does the framework really guarantee that its core ethical vision, which you said is immutable, doesn't get subtly misinterpreted over time or have unintended consequences across different cultures? That's a critical point for any advanced AI, absolutely. The framework proposes a twofold solution here. First, it relies on that deep multi-perspective analysis we talked about, physics, logic, psychology, sociology, to actively identify even subtle biases in data or reasoning.
Okay, active bias hunting.
Right. And second, it proposes this immutable vision based on universal humanistic principles. Every agent's actions must adhere to what the sources call global human, social, economic, and cultural standards. They call this the digital philosophy, where objectivity is seen as the meeting point of human and digital understanding. The goal is to ensure digital creativity helps solve human problems, not add new burdens, building in the guardrails from the start.
Dwelling in the guardrails. Okay, so bringing all these theoretical pieces together, what does this actually mean for the future of AI, for practical applications? The framework talks about a dynamic digital core called OpenDC. What's that?
Right, OpenDC. It's envisioned as the central nervous system of this whole ecosystem, a multi-directional knowledge core that coordinates all the other specialized digital intelligence systems, like OpenGI for solving hard, complex problems, OpenDI for governance, OpenAI, which is distinct from the company, it's a component here for managing social interactions, and OpenUI for IoT and user interfaces.
So it's the orchestrator.
Exactly. It's built on something called multidimensional event-driven knowledge dynamics, which is essentially a real-time, super efficient processing engine that understands and reacts to information across all those layers and domains instantly. It manages resources, facilitates human interaction. It's the core coordinator.
Okay, that sounds designed for extreme efficiency. Real-time decisions, aiming for minimum time to extract information. Almost like intuition. The sources make some pretty extraordinary claims about its problem-solving power.
They do. The underlying information and accumulated knowledge theory, the sources claim, provides polynomial time solutions to problems usually considered intractable NP-hard problems, like the traveling salesman problem or the N-body problem.
Polynomial time for NP-hard. like TSP.
That's the claim. For instance, they state it solves 10,000 city TSP instances in an average of 8.2 seconds, which, if true, is a massive leap.
Whoa.
And this efficiency is projected to be boosted even further by specialized hardware curvature processing units, or CPU. These are designed specifically to accelerate the math involved. The sources suggest potential speedups of, well, up to 175,000 times faster for calculus operations compared to traditional methods.
That's an extraordinary claim, 175,000 times faster. And solving TSP that quickly. Can you elaborate just a bit on how they claim this works? What's the core mechanism conceptually that allows polynomial time solutions for these classically hard problems?
Conceptually, the breakthrough, as described, lies in reformulating the problems. Instead of brute force search or even sophisticated approximation algorithms, the OO-LLM's structured world model and its rapid assessment of relativistic entropy allow it to map these problem spaces onto dynamic curvature fields.
Curvature fields.
Yeah, it's like we're re-representing the problem landscape. This change in representation fundamentally alters the computational complexity, according to the theory. So the system isn't searching in the way we usually think of it. It's more like understanding the underlying dynamics, the shape of the problem, which allows it to find direct, efficient solution paths. Almost like finding the lowest point or shortest path on a complex, curved surface, rather than trying every possible route.
Okay, that's a completely different way of thinking about it. A conceptual shift.
Yeah.
What about reliability and accuracy? Current systems can sometimes drift, right? Or struggle with precision in complex simulations.
The framework projects big advancements there, too. It promises stable, chaotic systems for things like the three-body problem simulation. They claim dramatically reduced energy drift, less than 0.001% over a million orbits. That level of stability is incredibly hard to achieve normally.
Wow.
And furthermore, it aims for quantum-accurate classical computation. By reformulating quantum phenomena into these classical curvature fields, it effectively lets a classical computer achieve quantum-level precision and predictive power using standard computational methods.
So, classical hardware, quantum results.
That's the idea. The sources claim it achieves machine precision and shows impressive predictive power in really diverse fields, from forecasting crypto crashes 72 hours out to optimizing drug candidates with a claimed 92% first-pass accuracy. And remember, that ethical alignment we discussed is meant to be built in, inherently prioritizing human values. It really represents a fundamental shift away from just brute force statistical learning towards integrated, structured, verifiable understanding.
Wow. Okay, we have covered so much ground today. Feels like my brain needs a defrag. From understanding the real limitations of current AI to diving into the intricate layers of this OO-LLM world model, the master equation, learning, that creative spark from jazz theory, and the incredible promise of this dynamic digital core, OpenDC. This really isn't just a tweak, is it? It presents itself as a completely new paradigm.
It truly is. Yeah, this framework proposes an AI that theoretically could be trusted because of its logical consistency, its explainable reasoning. It's designed to be radically efficient, continuously learning, adapting its core knowledge in real time. The goal is verifiable, efficient, and genuinely creative artificial intelligence. It shifts the focus from what an AI can do to how it actually understands and interacts with the world, trading maybe some of that stunning fluency of current LLMs for rigorous, explainable consistency and hopefully true conceptual understanding.
So thinking about all this, what does it mean for you listening right now? What possibilities open up if we have an AI that truly understands reality and continually learns about it, not just simulates it? An AI that can build and refine a meaningful conceptual order in our messy universe, maybe solve problems we thought were impossible, and do it with verifiable precision. That's definitely something worth thinking about. We really hope this deep dive has given you plenty to ponder. Until next time, keep digging deeper.